Okay. Okie dokie. Okay, so it looks like we have one question. Oh, that's curious. Okay. Alrighty, so our one question that we have, I guess it's two questions. So it looks like 50 and 51 from the homework. So I'm looking at those in Discord for us. So, question is asking if electron affinity is negative, is uh, is the anion more stable than the neutral? Okay. So I'm just gonna let's just put. Remember, electron affinity is this reaction, right? It is some atom, whatever. I'm putting A, gaining an electron, becoming a negative one. So if delta H is negative, whatever, what does that mean for us? Like, what do we remember that negative delta H means? Think back to thermochemistry, perhaps. Yeah, exactly. So this means it's exothermic. And if we remember, exothermic means releases energy. Or we could say has less energy after reaction. And so we have to remember that in chemistry, yeah, so stable always means the least amount of energy. The lower your energy is, the more stable you are. Highly reactive compounds have a lot of energy, they want to get rid of it. So stable things have the least amount of energy. So if we look at this, we see that this process gives off energy, right? It's exothermic. It's telling us that it's negative. And as a result, it has less energy than before. And so if it has less energy, that means it's going to become more stable. And so, since less energy is more stable, this tells us that the anion, whatever it is more stable than the neutral atom. So does that kind of make sense? So we it just kind of always remembering this big thing about why things react. Mostly it's to get rid of energy. We can force things to gain energy, of course, if we give it to them, but everything wants to get rid of energy. You guys didn't need to. Let's see. We'll get rid of that. You don't need to hear the random email noises. Yeah, for sure. So this, chemically speaking, something that is stable has the least amount of energy. Those two kind of definitions are synonymous, and that is always true. So the lowest energy state you can have is always the most stable. If we think about it, stable is the opposite of reactive, right? Something that is stable is not going to react. That's why our noble gases, really need a lot of work to get them to do anything because they're already stable, so they're not reactive. Um, only if your delta H for that is negative. So that's not necessarily true. So we remember for certain elements, it's actually an endothermic process to gain an electron. We saw that when we had to start occupying a new shell or start pairing off electrons, or if we were a noble gas, right? We kind of saw three like blips in this electronegativity trend, or electron affinity trend rather. So we saw all those noble gases do not want to get an electron. In fact, we see that in question 51. So let's go ahead and do that right now. So question 51 says that for bromine, delta H is negative. For krypton, delta H is positive. So this is exactly your question, Shane, with actual examples. And so we're this problem is just asking us to kind of explain why we think this is going to be the case. And it's kind of given us the hint that we should use electron configurations for this. So if we look at Br and Br minus, let me see, where's bromine on the periodic table? Probably argon based, yeah. So bromine is argon 4s2 3d10 4p5, right? And for bromide, we have this one. And from what we know, again, kind of with that idea that half filled is good, completely full is good, or empty is good. Like those three ideas. Exactly. So because this one is full p orbital, and this one is not full, that's why this one is better. And so if we compare krypton with krypton minus, we'll see krypton would be and I'm gonna kind of do this one. I'm not gonna write krypton 5s1 because that would just be quite silly. And so we're going to see here again, we have our last orbital is full. And this s orbital is not full. And so we already know our alkali metals that have these s1 electrons are pretty reactive, right? They explode in water or air, bursting into flames and fun stuff like that. So we're going to see that this one is preferred. It's better. And so that's why it's going to be unfavorable for krypton to gain an electron, but favorable for bromine to gain an electron. I guess I'll be consistent. I'll write better for this. All right, so it always just goes to this idea that full orbitals or empty orbitals are the better ones to have. And then, in the middle, you kind of have half-filled ones. But those are more for like d orbitals anyway, or p orbitals. For s orbitals, it doesn't really matter. There's only one, so having it half full isn't really that great. Okay. So it looks like that made sense. Okay. Okay, do we have any other questions on this? Does this kind of make sense? So we see that this is basically like favorable. Uh so all of these processes you can say there's a delta H for them. So anytime there's an energy change, um, that's going to be, you can consider that a delta H or a delta E. Doesn't really matter. So yeah, that's okay. So that's, yeah. So all of these would have a delta H or a delta E or whatever, um, and it's still the same trend. So if it's positive, it's endothermic, or as we're gonna see in Gen Chem 2, endergonic. Oh, which just means it's gaining energy, whereas endothermic is gaining heat. For us right now, they're the same thing. And then the opposite, negative, is going to be exothermic, right? And so that's why. Yeah, I saw. That's what I'm answering, Tyler. Come on, Tyler, you snail. You're back to snail now. Forget the turtle. You have gained an electron, and now you're back to a snail. Unfavorable process. Yeah, me too. Cheers. Okay, so we're good with that. Yeah. Okay, so, um, yeah, just I'll put that in writing. I mean, typically this is delta H because it's a reaction. Technically, we could also say delta E, change in energy. Change in energy that's positive is always unfavorable. You don't want to gain energy. So just like the same thing here, the lower energy you have, the better. Yeah, of course, ask as many as you want. Uh, I have 45 minutes left for you guys, so that's at least how long I've planned for this. So yeah, by all means, ask more. If there are any in particular you'd like to go over, I'd be happy to. But the answers are there already, so you can see them. Oh, my glasses need cleaning. Oh, goodness. Hopefully it's not all of those. Oh, I see, on the real exam. Let's see if we're going to get the question on 62. Which Kevin was right. That's not a good one to ask you guys right now. So let's see if that's the question we're going to get. 60, okay. Okay. Okay, yeah, Kevin, we can do that as well. Would you mind putting a picture of that in Discord so I don't have to look it up? Actually, you know what? I have it printed out right here. That's chapter. No, this is thermochemistry. Maybe this is here. Nope, forget it. You'll have to take a picture. Okay, so we're going to do number 60 as well. And then Kevin is going to get the other thing. Okay, so 60 is talking about this. Okay, it says it doesn't react with water, but they can react when it becomes either acidic or basic. Do we expect it to react with when it's acidic or basic? Which one do we want to choose? And then we need to write a chemical equation. So is this a metal oxide or non-metal oxide? All right, Tyler. Yeah, I don't know what's worse than a snail. I don't even know. Let's find scandium on the periodic table. Lo and behold, is it? Okay, well, scandium's right here, number 21. Right between calcium and titanium. I mean, if nothing else, titanium's definitely a metal, right? Oh yeah, you probably read it wrong as sulfur or something. Yeah, scandium. So, yeah, it's a metal for sure. Okay, thank you, Kevin. We'll deal with yours after. Oh, that's the pickle problem. I like that one. Okay. Yes, yes, yes. Okay. So then you're okay. Anyway, so yeah, this is a metal oxide. And so from that, we know that metal oxides are basic, right? We just will need to learn that. So if it's basic, that means it's going to react with what? Is it going to react with acids or with bases? Yeah, right. It's going to react with acids. So, I think this question specifically just says in a solution of H plus, so it doesn't really matter what acid. Okay, so you're probably just wondering. Yes, so Shane, this is actually exactly correct. So, what happens here is that this thing kind of breaks up. Oxygen 2 minus will react with H plus to form OH minus, which is your base. So, but let's go ahead and you're absolutely correct. That's why this stuff happens. Okay. Yes, exactly. So, I mean, you want to think it's positively charged, exactly. So, because OH would be a negatively charged one. Okay. So, we're just looking for some, generic acid. It doesn't matter what our acid is going to be. So remember, acids are just going to be a solution of something with H plus, right? It could be HCl. You know what? Let's choose an acid. What acid do we want to use? HCl. Okay. So we're going to give it an acid. That's just going to make things a little bit easier for us. So anytime you see these sort of like conceptual problems where it's like, predict this, blah, 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 it's always good to kind of just fake it by putting in real compounds. So we're going to see that's definitely going to be the case for the gas laws as well when we get there. Okay, so we're going to predict this thing is going to make scandium 3 chloride. Right? Remember, double displacement, we're not going to change our oxidation numbers. So scandium was 3 plus before, it's going to stay 3 plus. And then we're going to make, of course, our water as the other product. Let's see. Discord question, perhaps. Any acid would be okay. Yeah. You could use sulfuric acid, nitric acid. Doesn't matter. Any acid. You could have just left it as H plus, and you're just going to end up with scandium ions at the end, which is okay. That would work as well. But I think it's easier for us to kind of conceptualize the double displacement reaction if we actually have two compounds put together. And so if we were to balance this, we should get that. So if you didn't choose H plus or HCl, you could have just said H plus. And understand that you would just have scandium ions and water molecules. And you would have the same thing here. You would still need 6, 2, and 3 as your coefficients. And notice this is also charge balanced as an equation. We have 6 plus on both sides. So remember, if that's something you have to keep in mind, you should. So, but this would work. You could make it with sulfuric acid, whatever. Anything would work. Where the question just kind of, it's conceptual. It's not necessarily asking a concrete answer. Okay, so does that... so just kind of to review what we did, we identified it as a metal oxide first. for everyone who could read the scandium symbol correctly. Um, and then we understood that since it's a metal oxide, it's going to be basic. Metal oxides are always basic. And so it's going to tell us, or that tells us that it's going to react with acids. So bases react with acids, not with other bases. So we chose a random acid, or we could have just put H+, and then we just complete the double displacement reaction. And again, it's probably easier to do it this way. And yeah, you could totally choose any acid you want. So no problem. Are there any more questions on that one? Or anything that's like not clear about that? All right, so Kevin is going to bring us through the most particularly conceptual part of 82D. Let's hear it, Kevin. What's your question on that? Or do you just want me to like explain it, or what's going on there? Awesome. I'm glad that makes sense. Just so we know, this would be the like kind of net ionic equation right here. So it's exactly the same thing. It's just written as a net ionic equation instead of a molecular equation. Oh gosh. No. Let me just... So we've just basically gotten rid of chloride. But net ionic equations, remember, you could throw in whatever spectators you want to balance things out. So you could put nitrates in there, you could put iodide, something negative to balance it out, but it doesn't matter. So Kevin, what's going on with 82D? I mean, I guess I can just talk about it while Kevin writes something, or I'll just talk about it anyway. Okay, so the question is saying, so we had this pickle that was soaked with sodium, basically, in a salt water solution, and it absorbed the sodium into itself, and we threw some electricity through it and caused it to emit orange light. And so the question is asking, if we soak the pickle in a different salt, would we still get that same light emission? The answer for that is going to be a hard no. So remember that different elements have different energy levels. In fact, you can see in the table just on the second problem there, you have all these other elements giving off various wavelengths of light. So, I mean, we're kind of assuming that strontium is going to be displacing all of that sodium. I mean, I guess that's kind of the idea of that if we soak it for a long time, it's going to just, diffuse out and poof, now it's filled with strontium instead. And so strontium has its own set of wavelengths that it will emit based on the energy levels of strontium. So just remember that because there's a different number of protons in each element, the electrons are just held, more tightly, less tightly, and so they have all these different energy levels that are unique to each element. So 589 appears to be unique to sodium, so if we get rid of all the sodium, we should not see that light anymore. So that's kind of what that question is asking. Yeah, no calculation. The question is, would you still observe it, yes or no? So, yeah, that's it. So it's just saying, would you see this or not? I would say we shouldn't. And strontium actually is... I showed you guys kind of the flame testing, right? Strontium is red, whereas sodium is kind of orangish yellow. Regular fire is sodium colored. That would actually be a pretty interesting demo to do. Though I do not know how. Yeah, so I mean, I think you're kind of you're looking at it a bit too realistically. So I think the question here is just like pretend you swapped out all the sodium with strontium ions instead. So yeah. I would just not read too much into it. Yeah, I totally agree. In reality, yeah, there'd probably be some sodium still sticking around, but I think the purpose of this question was just to help you to kind of integrate the idea that the each atom has its own specific wavelengths that it's going to spit out once it's excited. Yeah, so I'm guessing that the soak for a long time part is supposed to be where we're getting the idea that it's replacing all of the sodium. So yeah, and that's no problem. So like, I'm not gonna be like, well, Kevin, blah blah blah, minus 10 points. No, don't worry, don't worry. So you're thinking. That's the purpose of this homework. I want you to think about stuff. That's why I'm giving you problems that like are not exactly like stuff we've done in class. Like all this stuff is to make you think about it, to help you kind of consolidate the knowledge that I'm supposedly passing on to you. So, um, yeah, I won't worry. I wouldn't worry about that, Kevin. All right, so we may have more questions coming in. Otherwise, I'll just draw various things. Okay, cool. Let's have a look at that. Ah, no, that's okay. So, this will be easy for me to answer. So, um, we just have to kind of understand what type of reaction is taking place here. So, all those oxides plus waters, these are going to be combination reactions. And so that'll just make barium hydroxide. If we were to put it with an acid, though, this would be a double displacement. So to answer your question, thankfully this is one I can answer very uh, bluntly. When you're combining it with water, that is a combination reaction, so you're just making one product. When you are doing a acid-base reaction, that's always going to be double displacement, so you're going to get two products. So let's see. So this is just, base plus acid. This is base plus water. I guess I could write water. So that's it. Okay, so while we're typing our next question on there, I will continue my drawings. So let's see, sulfur is somewhere over here, yeah? Oh no, I've deleted the periodic table. Here, we'll fix that. Yeah, rules to follow are always nice. Yeah, rules make things nice and easy for us, don't they? Ah, good. I'm glad someone appreciates my drawings. But just to be clear, I will only make fun of people if it's okay. So if it's too much or whatever, let me know, and I won't make fun of you anymore. And I'll just stick to making fun of Shane and Kevin. No worries there. Is that where scandium is? I hope so. Yes, it is. Good. All right. Anything else you guys want to go over? Yeah, that's okay, Shane. Go ahead. Yeah, mollusks are pretty cool, aren't they? But this particular one is Tyler, who had lost his shell, his scandium based shell. Yeah, so don't forget there is a practice exam up. It is on Canvas as well as in the extra resources thing on Discord. Um, it's in a rich text. That's interesting. All Word should still open that. Here it is. Okay, so let's see if we get any questions out of this. Mm-hmm. Let's see if any of these are that tricky. Okay. Well, how about we 14 and 18. Okay, we can do that. Sure. So, when we look at isoelectronic series, we have to remember that more positive means smaller, more negative means bigger, right? So, let's go ahead and look at 14. So I'm going to switch this over to that window instead. 1 second. That's it. Okay, so we're looking at this one right here, number 14. So it's asking us to do it in increasing order. So we're going to have, basically that means we're going to put our smallest one on the left and our biggest one on the right here. Let me see if I can't do it this way. Oh. That's not kind of what I wanted. Well, it kind of works actually. 14 are we doing? Yeah. Okay, so let me make it a little bit smaller. Okay, here it is. So we're doing number 14. So we are going to want to put our smallest one on the left and our biggest one on the right. And so we want to remember that the most positive one is always going to be the smallest for an isoelectronic series. So the reason for that is they all have the same number of electrons, but we're now basically ordering them in their order of protons. So from this list of all those elements there, calcium has the most protons. And since all of these have the same number of electrons, calcium having more protons is going to pull electrons in towards it even more, right? And then, it's going to just keep going that way. So we know our smallest one should be calcium on this list. And again, we're basically making this from most positive to least positive. That's kind of the order that it will always be for small to large. And so the next one should come potassium, and then we should have our neutral one and then our negative one. So we are going from most positive to least positive. Or in that case, it's negative. So it looks like the answer should be B for that one. Oh, I'm sorry. That's a little bit... There we go. See if we can get all of that in there. So just remember, more protons means more pulling of electrons. The more pulling you have, the tighter things are going to be. So you're going to have a smaller atom. Okay, and then you want to do 28 as well. Okay, cool. So which of these is an isoelectronic series? What is the definition of isoelectronic? Same number of electrons, exactly. So looking at all of these, there's a couple we can get rid of right away. Actually, like 3 of them we can get rid of right away. By understanding that, A, B, and E there would all have different numbers of electrons. Right? Fluoride and chloride and bromide and iodide, they all have the same charge, but they're different elements. So they all have gained 1 electron, but they had different numbers to start with. So they're still going to have different numbers of electrons. Same thing with B. They all have gained 2 electrons, but since they all started with different numbers, they'll still have different numbers. And with E, they're different elements. Different elements have different numbers of electrons. So that narrows it down to 2 choices. We have C, which is boron and silicon and all that fun stuff. And then we have D, which is oxygen, fluoride, neon, and sodium. And so isoelectronic series, we're going to be able to kind of follow them in a line on the periodic table, assuming the charges are done correctly. So if we're looking at... Creatures just scratching the carpet under the desk. We're looking at kind of two kind of blobs. We're looking at this one, or we're looking at this one. And so we're for isoelectronic, we're looking at, it's going to be D for sure, but we're just looking for which ones are the same number of electrons. If you look at D, all of those have 10 electrons, and so that's why D will be the correct answer. Good point. Goodbye test. Poof. So we were basically comparing these two. So we had boron ions and all that fun stuff, and then we had this horizontal group. And so the horizontal group is going to be how we define an isoelectronic series. So if you wanted to add on to that series, we could have included nitride. We could have thrown that in there, or magnesium. We could expand it horizontally. This one, however, is not going to be isoelectronic. Tellurium 2- would have 54 electrons. Boron 5- would have 10 electrons. So definitely not the case there. Okay, so that one's just kind of a, do we remember what the heck an isoelectronic series is? Oops. Oh my gosh, go away, periodic table. This one. Correct. They have to be horizontal. And they have to be charged. So E would also be horizontal, but those are not charged, so they don't have the same number of electrons. So, like, the closest one to the correct answer would be E. So D is correct, but E is like the closest. Otherwise, the closest wrong answer. Exactly. Yeah. So that's why like A and B there are actually B is not there, but A would be an example of the preferred charge for a group. So that would be all the halogens with their -1 charge that they enjoy so much. B doesn't. I mean, B is weird, so it's another like kind of diagonal series. No, it's horizontal, but they're all the same charge. So that's not the idea. Okay. Anything else that comes out at you on that one? Or on the exam? I hope so. I haven't written it yet, Shane, but I'm hoping to make it of similar stuff. Well, so it would be exactly the topics that are covered on this practice exam. So yeah, it's the light stuff. It's the like here would be some of the light stuff. Let me put this one up. This would be an example of light stuff. That could be like a question on the exam. So if we look at number 12 here, it's saying which of the following is going to be the shortest wavelength. And so we have kind of 4 options there. So shortest wavelength means what in terms of energy? Does short wavelength mean high energy or low energy? I guess that's what I'm asking. Yeah, we're looking for the highest energy. And so since this kind of chart, our axis is energy, like the y-axis there is energy, we're looking for the one that has the biggest change in the y-axis. It's not really a graph, it's kind of a one-dimensional graph, but so it's going to be A, right? We're going to see that A is our biggest energy change. And so that would have the most energy associated with it, and therefore would be the shortest wavelength photon. Let's see, what else do we have? Yeah, there's some, rudimentary calculate the, use this equation up here, wherever it is, blah, 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 we can use this thing. Ah, you're thinking too much. For this, we just have to look at how big the arrow is. So the arrow for A is remember this up and down thing means the amount of energy. So if we just look at how tall A is compared to B, this is a bigger arrow. Bigger arrow means more energy. Yeah. If you really wanted to double check that, you could totally have done the equation where you do 3 minus or 1 minus 1/9 and then 1/25 over 1/4. You could totally do that as well. So if you had a bunch of time, yeah, you could totally do that. However, actually, I mean, we don't even have to do it that more difficult. I don't know what I'm trying to say. Okay, I'll show you. So we have a transition from 3 to 1, and what is the other one? 5 to 2. Doesn't really matter which direction they're going. It's just which one has more energy. So one could be released, absorbed, doesn't matter. If we think about this, this is going to be 1 minus 1/9. This is 1/4 minus 1/25. If you do the math, 8/9 is going to be bigger than... Oh God, I don't want to do this math, but I'll do it. Actually, this will be 0.21, right? Yeah, and this will be 0.89. Boom, more energy. Bigger number. Technically, of course, you would multiply this by the 2.18 thing. But, yeah. I mean, since we're just comparing it, we don't need to actually calculate it. So this is the only thing that's different in those two equations. So if you're, confused about the graph or whatever, you could always just calculate it. I think this is actually how I did some of your homework stuff. Oops. Like some of the stuff on the homework key, I did it this way, where I just calculated the 1 over n minus 1 over n, rather 1 over n squared thing, rather than actually comparing, because forget it, we don't need to do that. Yeah, so add that, I guess, to your toolkit of secret shortcuts you can use. Okay, well, I mean, it depends if you like the visual, like graph, or this thing. Okay, but let's see, what else do we have on this practice exam? Let's see, quantum number stuff. Plenty of that on the homework, so you should be. Well, you all just got to take OChem instead. So, let's see what else could be tricky on this. Don't we all? Okay, let's look at number 23. So this one is going to be the second ionization energy. So first ionization energy was what? The one that we did the trend of. What did the trend say? What was the definition of ionization? So ionization is removing an electron, right? So the first ionization is going to be removing the first electron. So second ionization is removing the second electron. So yes, you are going to be correct there. So we're looking for one that has already lost an electron, which would mean it's positively charged. And we're getting rid of a second electron. I mean, this one just doesn't even make sense. Like, plus minus turns into 2 plus. Doesn't work that way. Yeah, so we're looking for D here on that one. So it's losing a second electron. That's what it's showing. What else do we have? I guess that would, be some sort of like second electron affinity, yeah. That's I mean, I guess, so you, I mean, it definitely is some sort of electron affinity, right? Let's go to this here. So, electron affinity is usually just to gain one electron. I've never seen something that is a like second. Oh, what do you know? There is one. Here, I'll show you all what I'm looking at. Wait, why isn't this working? It's clearly something that is not common, but lo and behold, you're right, it exists. Here we go, we're on Wikipedia now. So it does look like there is a, second or third electron affinity for a few things. But by and large, it looks like most electron affinity data that have been collected are for just one electron. So, like for aluminum, it's just to make it aluminum minus. So yeah. So it looks like for this second and third one, there is something, but not a lot of data has been out there for that. So, what is reference 69 on this? By the way, Wikipedia is like your best friend in chemistry. It has all the data, like you could always find on anything. In high school, I'm sure you've been yelled at a cajillion times never to use Wikipedia, blah, blah, blah. Wikipedia is the enemy. No, it is our good friend. No one is going to go in and just change this for no reason. And the editors would be on their ass anyway, like immediately. So, yeah. Cool. Anything else you'd like to go over? Yes, true, exactly, yeah. So if you're ever writing a research paper, totally just go right down to the references and use those instead. Yeah, bypass the old Wikipedia thing. I definitely did that quite a few times in my day. So, back when I had to do stuff like this. Cool. Alrighty, what else do we have you want to go over? If anything. I have a little over 5 minutes left. I was just thinking about this transition stuff. I believe n equals 2 to n equals 1 is going to be more energy than even n equals 100. Doesn't matter. If we think about it, that's going to be versus this thing, right? This is essentially 0.25, right? So going to level 1 is always going to be more energy than anything else. Perhaps another thing, a toolkit you can have. Anything that involves the first energy level to any other energy level will always be more energy than any other transition. Energy gaps for you. Alrighty, so I guess we're out of questions, which is okay. Let's try and write your exam eventually. Post your homework for Sunday night viewing, or Sunday day viewing rather, whatever you like to do. the answer key, that is. So, sure. Ooh. You really want to do that, Kevin? So, it's not only a factor of where things are on the periodic table, but also how many oxygens are involved. So we're going to see that stuff that is... let me see here. What would be the best way to describe this? So we want to consider stuff that's more, up and to the right. Again, being more electronegative is going to be probably less acidic. We want to think of less electronegative ones. The oxygen is going to steal more electron density. This is something that I don't want to go over until OChem. So let's... because it deals with things like polarizability, which are not trends that we've talked about so far, that we typically aren't even going to need right now. Actually, we'll probably talk about this in Gen Chem 2, because there's multiple chapters on acid-base equilibria in there. And so I think it'll be better to focus on those later. So let's just skip that for now. Yeah. We're going to see, for example, like... sulfuric acid, very strong acid, of course, comes from SO3. And for example, you also have phosphoric acid that comes from this particular oxide. Actually, it's better to write it this way. Usually it occurs as a dimer. And we're going to see, chemically speaking, this one is going to be more acidic than the phosphoric acid. But we also have to consider that, the phosphoric acid is triprotic, and each of those will have their own acidity level. And so, it kind of... I liked that question, but it brings too much into equilibrium chemistry, where we have multiple protons that could come off, and all of those would have their own acidity levels. And so it's like, are we comparing the overall molecule or individual protons? And it just goes way too messy that I didn't want to cloud our minds with. So, yeah. But suffice it to say, it deals with electronegativity and size. So, polarizability, fun stuff. Alrighty, cool. Guess that's it for today. So I will see you all on Tuesday then. I'll post your homework key later, maybe tomorrow, maybe Saturday. So it'll be up for you guys on Sunday. Don't forget your homework is due Saturday night. So have fun. Alright.